Okay, so continuing with lecture 4 on, and in particular the part on limits and colimits. So I'm hoping that you've watched the previous part where we defined limits rather carefully, and then we quickly said how you define colimits as a sort of opposite version of limits. And we gave some examples. There are many more examples which are really worth seeing, and one good place to find lots of them is in Lenny Townman's notes. The link is in the PDF document. So what I want to do in this segment is to talk about some sort of more interesting examples. So we've seen some rather familiar things. I guess the most exciting thing we got to is maybe kernels and co-kernels. And so you might wonder, we've developed all this exciting machinery, but can we not do anything more with it? So I'll try to do some more interesting examples. And then I'll talk a little bit about where some of the terminology comes from and this kind of thing. So this segment is sort of general odds and ends. So fibered products and co-products. So, I mean, products and co-products are a little bit boring in some, well, not always, but they're generally a bit boring. Products are just what sort of, I don't know, like Cartesian products in set. And co-products are like disjoint union in set. But fiber products and co-products can be more fun things. So the basic diagram we're looking at is, what should we start with? Let's start with co-products. Or fiber co-products. So here our diagram is going to be like this. It's going to have three objects, say 1, 2, and 3. And it's going to have two morphisms, say morphism A, which goes from 1 to 3, and morphism B, sorry, A goes from 1 to 2, and B goes from 1 to 3. Okay, so, well, let C be a category, and F a diagram of shape I. I'm just going to write from I to C. Then the limit the colimit of this diagram, F, is called fibered coproduct of F of 2 and F of 3 over F of 1. Okay, so I'm just mentioning this is the standard terminology. Of course, this terminology is not great because it really matters what the maps are, otherwise you get different answers. So notice that, why did I take the colimit? You could also take the limit of a diagram of this shape. That's a completely legitimate thing to do, but it's a boring thing to do. Remember, this category has an initial object. So the limit of a diagram of shape I will just be f of 1. So nothing very interesting happens. The colimit is where all the business is. So let's do an example. This is C is the category of topological spaces, and say F of A and F of B are inclusions of open subsets. Let's say open and injective. Okay, so then this fiber coproduct, so limits and colimits don't always exist, and the same is true with the diagram is of this shape. In this case, the colimit does exist. And it's given by gluing F of 2 and F of 3 along the open subset F of 1. Okay, so that is what it is. So I'm reluctant to try to write out the proof of this on the board because it is kind of a mess. So what I recommend is that you first do a slightly simpler case. You do the case where C is just the category of sets, and F of A and F of B are both injective, and then work out what happens there. Basically, you'll take F of 2 and F of 3, these sets, and then you'll sort of glue them together, but you're identifying them along the subset F of 1. in the category of topological spaces, you can do essentially the same thing. Okay, so this is a bit more interesting now. We can see how to use fiber coproducts to glue together topological spaces along open subsets. So we can also do fiber products. So let's do this. Okay, so now we're going to take essentially this diagram but with the arrows reversed. But let's write it out sort of more concretely. Okay, so now if f from I to c, this is a diagram of shape I, then the limit is called the fiber product. Of f of 2 and f of 3 over f of 1. Again, this terminology is not precise enough because it doesn't specify what the maps are. Sometimes there's an obvious choice of map and that doesn't matter too much. Other times this is a wonderful source of confusion. Okay, so for example, let's take C to be the category of sets, and then okay, so we know how products work in the category of sets. You can naively think of them just in terms of Cartesian products, pairs of elements. So then, and it turns out the fiber product has a sort of similar interpretation. So then, say the fiber product, so the limit of a diagram F, so this fiber product is given by the following thing. So you take the set of, say, x comma y, in the product f of 2 plus f of 3, such that, okay, so f of 2, let's draw out the diagram here. And here we have f of a. Here we have f of 3 as well. Here's f of b. So we have the usual Cartesian product, pairs of elements. What we want to require is that f of a evaluated at x is equal to f of b evaluated at y as elements of f of 1. Okay, so in other words, it's sort of a restricted version of the Cartesian product. You're taking the product of sets, but then you're only interested in the parts which have the same image in some third set. Okay, so there are, maybe there's another, so this, one can sort of generalize this to, one can also do this on the level of topological spaces. So I'll make a little more space by erasing my big messy diagram. I think the last examples I want to do use some machinery that we haven't got to yet, so I'm going to leave the last few examples to the PDF. Okay, so we've seen the definition of fiber products and fiber coproducts, and we've seen an example of each. There are very many more which are very worth studying. Okay, so I want to do a quick guide to terminology at this point. Because the terminology around limits and colimits can be very confusing. Essentially, they've appeared in various different versions, sort of more general as time has gone on, and the language has sort of evolved or not with them, and the result is a little bit of a mess. So limits. So what we've called today a limit is often called an inverse limit. Or a projective limit. What we've today called a colimit, this is traditionally called a direct limit, or an inductive limit. So the fact that limits and inverse limits and colimits and directed limits is terribly unfortunate and confusing. But unfortunately, this is the terminology that is in use, so we're kind of stuck with it. So how can we sort of try to remember these, or at least, I mean, yeah, I guess learning the old languages is a thing I guess that one sort of has to do, but at least to remember which is which between limits and colimits. So some examples of things that are colimits are co-kernels, as we've seen, co-products, co-equalizers, and codomains. Notice they all have co at the beginning. This is very useful. Examples of limits. Well, essentially, take all the same thing but cross the co-op. So kernels, products, equalizers, and domains of functions. Okay, so the way I remember which is which between limits and colimits is I remember that these things that have co in front are colimits. So I remember that there is a definition of limit and a definition of colimit. I often forget which has the initial and which has the terminal object in. So the way I remember them is I remember, for example, that co-products, like disjoint unions of sets, for example, are examples of colimits. That will allow you to reconstruct what the definition should be, and then you can hopefully unconfuse yourself. Okay, so the very last thing I want to do about limits and colimits is a sort of silly thing, but we spent quite a bit of time. Well, we had Yoneda's lemma in the first segment, which was probably kind of confusing. It's a complicated thing when you first see it. And we've also spent a lot of time defining limits and colimits, but I want to illustrate that these are useful things by giving a very fast definition. So quite a lot of you will probably take an Algebraic Geometry 1 course this coming semester, where you learn a definition of an algebraic variety, and then maybe if you get on with that kind of thing in the second semester, you'll take an Algebraic Geometry 2 course, and then you'll learn the definition of a scheme, and then you'll spend many weeks learning many basic things about them. But the nice thing is that with the machinery we've developed so far, we can give the definition of a scheme in just a few lines, which is kind of fun. So just for illustration, let's do this. So definition, so define C ring to be the category of commutative unital rings. Define affine schemes to be C ring op. And then we have F, I'm going to write for the category of functors from affine schemes op to set. Okay, and then by the Yoneda embedding I have, this is my Yoneda, gives me a fully faithful map from the category of affine schemes to this functor category, and then the category of schemes is the smallest subcategory of F, which, and now I have to put on a few conditions. So the first condition is just that it contains the affine scheme, so that's not such a crazy one. When I say contains F, I mean the image under the Yoneda embedding. Is closed under hybrid coproducts along open immersions So I also need to tell you what an open immersion is. So this is a formally étale. So this is This is a very short definition you can find in the stats project. But it's only a few lines to write out. There should be a monomorphism. And they should commute with all limits. So limits in the sense that we've defined here. Okay, so, well, I could use another board to actually spell these things out, but that would be a waste of time. My point is not that this is the correct way to define schemes and now you should skip the algebraic geometry course. My point is rather that whilst we've been spending quite a bit of time doing these sort of abstract nonsense definitions with the Oneida embedding and limits and colimits, once you have all that machinery in place and you're sort of comfortable working with it, then concepts which sort of seem scary and intimidating can actually be presented in a sort of very, very efficient way. Okay, that's the end.